We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live, streaming in real time around the globe of them watching all of this. Take a look at this.
There are images that show us beauty, and there are images that show us truth. This one does neither. At first glance, it looked like a failure, a photograph that refused to focus. But behind that blur was something extraordinary: motion captured at the edge of physics, light collected from a traveler that has never belonged to our sun. Every pixel in that image carries history, the trace of an object older than Earth, crossing our sky for the first and last time. So, what does this image actually reveal? Holding still what refuses to stay still. Capturing 3. Atlas isn't like photographing an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects even a few seconds of light, the object has already traveled thousands of kilometers through space. A single frame would show nothing but a soft streak, a comet-shaped guess, stretched by its own motion. To overcome that, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time. The stars in the background blurred into trails, but 3I Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out, a precise balance between the comet's speed and the telescope's pursuit. Even then, one exposure wasn't enough. At magnitude 17, the comet is barely visible to the sensor, so astronomers stacked multiple long exposures, aligning them until the faintest signal added up to something coherent. Atmospheric tremors, instrument vibrations, even temperature changes, all had to be filtered away. The shape that remained was fragile but consistent, a faint cylinder of light that moved faster than our focus, yet slow enough to be caught. What we're looking at isn't just a photo, it's time made visible. Every pixel carries minutes of motion, compressed and rebalanced until stillness could exist where it shouldn't. The image shows what happens when technology and patience bend together to meet something the universe never meant to be seen clearly. 3I Atlas didn't stop for us. We simply learned how to move with it. Shape without surface. In the image, 3I Atlas doesn't show a surface. There's no crisp edge, no nucleus shining at the center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself, smooth at one end, uneven at the other. The elongation is unmistakable. It's not round and it's not random. It holds a structure that almost looks deliberate, but too faint to confirm. That shape has puzzled everyone studying it. If it were an ordinary comet from our solar system, we'd expect a rounded head and a tail tapering behind it, a classic teardrop pattern shaped by the sun. But this isn't that. The frame shows a body that seems evenly stretched, almost like a cylinder, without a clear tail direction. The brightness peaks slightly toward one side, which suggests a rotation axis angled toward the observer. If that's correct, the comet could be spinning rapidly enough to blur its features in the exposure, the way a long shutter smooths moving water into a flat surface. It's also possible that what looks like shape is actually brightness variation, light reflecting off an uneven surface made of dark carbon and silicate dust. 3I Atlas's albedo, or reflectivity, appears extremely low, meaning it absorbs most of the sunlight that hits it. The faint light we do see isn't emission, it's reflection scattered through a thin layer of ejected material. That's why the image feels soft, as though it's not focused on a solid body, but on a cloud shaped by motion. Still, the proportions remain too consistent to dismiss. Across stacked frames, the ratio of length to width stays nearly constant, hinting that the elongation is real. Whether that's a single, rotating nucleus or a cluster of fragments held close by inertia is still unclear. For now, the shape stands as a physical clue wrapped in uncertainty, a solid hidden in light, geometry without surface. The color that isn't there. When astronomers processed the raw channels of the 3I Atlas image, they found something curious. No real color. Most comets, even faint ones, show at least a hint of tone: a greenish halo from cyanogen gas, a yellow-white tail from reflected sunlight. But 3I Atlas gives almost nothing. Across visible wavelengths, its spectrum flattens into a neutral gray, a silence in color that says more than a bright signal ever could. This absence tells us the object isn't actively outgassing in any strong way. If water or carbon compounds were being released in quantity, they would glow faintly under ultraviolet radiation, painting the image with trace color ban. Instead, what we see is pure reflection, sunlight bouncing off a surface so dark it barely returns a measurable fraction. That's why it appears almost monotone. It's not colorless because it lacks material. It's colorless because the material absorbs nearly everything. The numbers confirm this. The apparent albedo sits at an estimated 2 to 3%, darker than asphalt. Only the faintest scatter escapes into the visible rain, smoothed by interstellar dust that coats the surface. Over millions of years drifting between stars, that dust has been bombarded by cosmic rays, baking carbon molecules into complex organics. These tholins tint the surface in deep reds at microscopic scale, but when seen from a distance, they combine into neutral gray. The color cancels itself out. Even the telescope's filters, near-infrared, visible, ultraviolet, show the same quiet profile. A gentle rise in infrared suggests cold carbon dioxide ice just beneath the crust, but it's weak, barely above the noise floor. The result is an image that feels stripped down, like the light has been reduced to its simplest form. For an interstellar object, that lack of vibrancy isn't emptiness, it's age. This is the color of endurance, of a surface that has traveled for eons without renewal. 3I Atlas doesn't display color because it no longer needs to. What remains is the faint equilibrium between sunlight and memory, light reflected off something too ancient to shine. Photons on the edge of certainty. Every faint comet challenges the edge of what our detectors can prove. 3I Atlas lives right on that border. In its raw data, the comet is barely a presence at all, a whisper above background noise. When you zoom in close enough, even the sky seems louder than the signal. But the difference between random static and a real object comes down to consistency. Real light behaves with intent. It repeats, aligns, and holds pattern where chaos can't. That's what makes the 3I Atlas image meaningful. Across exposures, the faint streak appears in the exact same coordinates, its brightness curves stable despite atmospheric shifts and thermal noise. That repeatability is the only reason astronomers can call it real. The data isn't just faint, it's fragile, requiring mathematical reconstruction to separate photons belonging to the comet from those arriving by chance. It's less like taking a picture and more like building one photon at a time. Each pixel in the composite represents the sum of hours of signal gathering. In every frame, software models the sky background, subtracts cosmic rays, and averages the remaining values until a contour begins to form. The final image exists only after millions of calculations reduce chaos into geometry. It's an image at the threshold of certainty, not sharp enough for comfort, but too consistent to dismiss. In physical terms, that uncertainty makes sense. The comet's brightness fluctuates with its rotation, and sunlight scattering off its rough surface introduces micro-variations that blend into noise over distance. Even light itself struggles to define the object. A photon leaving 3I Atlas arrives already exhausted, red-shifted by motion, diluted by distance, and spread thin across detectors that only barely register it. The result is an image that feels incomplete by design. It mirrors the way the universe actually reveals itself, not in clarity, but in persistence. Every pixel in the frame is a vote for reality, cast by a photon that traveled millions of kilometers to be counted once. 3I Atlas is visible, not because it's bright, but because it refuses to disappear entirely. When data refuses familiar form. Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. The algorithms that measure coma curvature, nucleus brightness, and tail direction couldn't settle on a pattern. The numbers diverged depending on which model was applied, each insisting on a different shape. In data terms, that kind of disagreement usually means one of two things. The target is unstable, or the physics behind it doesn't fit existing templates. Most comets follow predictable equations. Solar heat drives sublimation, jets of gas push outward, and dust streams along the sun's vector to form a tail. But 3I Atlas breaks that logic. The faint elongation in its image doesn't align with the solar direction at all. It tilts several degrees off, suggesting the body isn't venting material uniformly. It could be rotating rapidly or shedding particles from a fracture rather than an active jet. Either way, its symmetry refuses to match the models built for local comets. Some analysts compared the brightness pattern to 2I Borisov, the last confirmed interstellar comet. Borisov displayed a textbook coma and tail, even when it was still far from the sun. 3I Atlas, by contrast, behaves more like 1I Oumuamua, an object with no visible coma, only reflected light. Its blur lies between the two. Too diffuse to be a solid asteroid, too clean to be an active comet. That ambiguity makes classification nearly impossible. Spectral measurements reinforce the confusion. No strong emission lines appear, no water, no cyanide, no carbon monoxide flares. The spectrum is flat, except for a faint dip in the near-infrared, possibly from carbon dioxide ice sublimating under minimal heat. It's as if the object is waking slowly, testing how much sunlight it can absorb before losing structure. When data stops fitting patterns, it forces observation to become interpretation. 3I Atlas sits in that gap, part comet, part fragment, part unknown. The picture we have isn't wrong, it's just incomplete, showing us a kind of object our instruments weren't built to categorize. For now, the blur stands as evidence that even within physics, form doesn't always mean familiarity. The math behind the blur. When an image can't explain itself, mathematics takes over. The frame of 3I Atlas is too faint, too ambiguous for traditional analysis, so scientists turned to numbers to extract what the light couldn't say directly. Every pixel in the photograph becomes a coordinate, every shade of gray a probability. It's less about seeing the comet and more about understanding how the light must behave for the image to exist at all. The first step is motion modeling. By plotting its position across consecutive nights, astronomers determine its angular velocity, a precise measure of how much sky it crosses over time. That rate, combined with the object's distance from the sun, translates into a real velocity of roughly 12 kilometers per second, confirming its hyperbolic trajectory. It's moving fast enough that no gravity in the solar system will ever pull it back. Every calculation reinforces what the blur already implied. 3I Atlas is just passing through. Next comes brightness fitting. The faint gradient along its length is modeled to estimate orientation and reflectivity. Simulations show that if the nucleus is elongated, perhaps several times longer than it is wide, then a slow tumble could recreate the uneven brightness we see. The rotation would cause one side to catch sunlight more efficiently before fading again, producing the soft oscillation embedded within the blur. That variation is tiny, almost invisible, but the math detects it where the eye can't. Even the blur itself becomes measurable. By deconvolving the image, reversing the distortions caused by optics and atmosphere, researchers calculate how much of the elongation comes from motion versus shape. The result shows that while tracking smoothed the comet's movement, residual drift still contributed to its stretched appearance. In other words, the blur is part real, part consequence of chasing something that can't quite be caught. This is what modern astronomy often becomes, a dialogue between data and deduction. The image shows only uncertainty. The equations describe why it should look that way. Together, they turn a faint smear of light into a complete physical statement. Position, speed, rotation, and the quiet mathematics of a body slipping through our focus on its way back to interstellar dark. Distortion or discovery. Every image has ghosts. Even with the most careful calibration, sensors bend, optics distort, and data finds ways to imitate structure that isn't really there. When the first processed image of 3I Atlas was released, that question appeared immediately. How much of what we're seeing belongs to the comet, and how much is the instrument trying to keep up? At the faint brightness levels 3I Atlas occupies, distortion becomes part of the data. Cosmic rays striking the detector can leave small flares, while fluctuations in readout voltage stretch or compress faint signals. Over hours of exposure, these tiny errors accumulate and masquerade as shape. The cylindrical blur that defines 3I Atlas could in part be that, a subtle elongation caused by the camera compensating for motion and noise simultaneously. Even the telescope's tracking accuracy, impressive as it is, cannot perfectly cancel the object's velocity. A 1-pixel drift per frame, multiplied by dozens of frames, creates a false extension easily mistaken for structure. But not all anomalies vanish under scrutiny. When the images were independently processed using different software pipelines, the same general elongation remained. The angle of tilt, the brightness gradient, even the faint suggestion of tapering, all persisted across systems. That level of consistency argues against coincidence. If distortion were the cause, its signature would shift between instruments. Instead, the shape repeated itself, stubborn and quiet, as if the comet's geometry was asserting itself through the limits of observation. Spectroscopic data offers a small clue. A slight reddening toward one end of the blur matches how sunlight would scatter off a rotating, asymmetrical body. It's not proof of structure, but it's enough to give the shape credibility. This is the tension that defines astronomy at the threshold of detectability. Every feature we see could be discovery or distortion, signal or noise. With 3I Atlas, the distinction blurs, quite literally. The comet exists somewhere between what's captured and what's imagined, its form shaped as much by light as by the struggle to interpret it. The object that escaped definition. At some point, the discussion around 3I Atlas stopped being about what it looked like and became about what it refused to be. Every attempt to classify it pushed against the limits of existing categories. It wasn't a traditional comet, lacking both tail and coma. It wasn't an asteroid either, since its light curve varied too smoothly to come from a rocky surface. The image presented something in between, a blur that resisted interpretation, an object defined by the fact that no model could describe it cleanly. The data now paints a picture of contradiction. The brightness curve remains stable enough to suggest a single body, yet the slight asymmetry hints at motion within motion, perhaps a slow tumble, perhaps fragments, orbiting a shared center. Its trajectory confirms an interstellar origin, a hyperbolic path that ensures it will never return. That certainty of escape is, paradoxically, the only thing about it that feels familiar. Astronomers have seen ambiguity before. 1I Oumuamua was too sharp and fast. 2I Borisov was almost too typical. 3I Atlas sits between them, as if bridging the gap, neither solid rock nor classic comet, neither silent nor active. It behaves like a memory of both. Its faint cylinder of light is the signature of something that exists just beyond the boundaries of resolution and taxonomy, a reminder that our categories are only conveniences, not truth. Even the image itself seems to echo that duality. The blur is both evidence and absence, a confirmed detection that withholds its identity. It forces astronomy to confront the uncomfortable idea that seeing isn't the same as knowing. For centuries, telescopes have given us sharper, deeper views of the cosmos. But objects like 3I Atlas reveal the limits of that progress. Sometimes, the clearest image possible is one that refuses to resolve. So the blur remains, not as a flaw, but as a fact. The object escapes our definitions not by hiding, but by existing in the thin space between them, where physics still operates, but language begins to fail. A visitor measured only by its blur. When the light from 3I Atlas finally fades from our senses, the photograph will remain a faint smear in the archive, a record of something that passed too quickly to ever be seen clearly. In most branches of science, such an image might be dismissed for lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about 3I Atlas exists inside that faint streak. Its velocity, its trajectory, its brightness curve, its distance. From that single, unresolved shape, entire models emerge. How it spins, how sunlight touches its surface, what minerals might make it reflect the way it does. The image's weakness is its strength. It forces meaning to come from physics rather than appearance. We don't know what the comet looks like, but we know what it is doing and where it is going. Soon, it will leave our system entirely, receding into the same dark it came from. No future telescope will see it again. Its orbit is unbound, its direction set. The blur we have now is not the beginning of study, but the end of accessibility, the one clear intersection between human observation and an object that belongs to interstellar space. That is what makes this image different from any other comet portrait. It's not a picture of a destination. It's a snapshot of passage. A body formed under another star has crossed through ours, leaving nothing behind but the proof that it was here. The photograph doesn't try to beautify it or even define it. It simply shows light doing what light always does, traveling until it's caught, then disappearing into memory. In the end, that's all the evidence astronomy ever holds. Traces of things already gone. 3I Atlas was never truly seen. It was measured by its blur, and that perhaps is the clearest image we could ever hope for. That's it for today. Let us know your thoughts in the comments down below. Don't forget to like and subscribe to stay up to date with all things 3I Atlas.